In the last video, what we looked at was how we could calculate the area under a polar curve using a little bit of calculus. And now we want to do something similar, but with arc length. So what we're going to do in this video is we're going to take a section of a polar curve, maybe it does something like this, and say from between two angles, say theta equals alpha and theta equals beta, we want to understand what the length of the curve is. So like, what is the linear distance that constitutes this right here, this section of the curve? And so that's what we're going to be looking at. We're going to see how we can derive a formula for arc length, but now in polar coordinates. Okay, so let's start with, let's start with recalling what we learned, or how we can compute arc length of a parametric curve. So let's recall here. Arc length of the curve, of the parametric curve, x equals x of t and y equals y of t, from, I'll use alpha and beta still here. For t between alpha and beta was the following. We learned that, so we'll call it L for our length, is the integral from alpha to beta, the square root dx dt squared plus dy dt squared dt, right? We learned that this was arc length, and we want to now start here with something that we've already derived and derive a formula for arc length in polar coordinates. So I'm going to do kind of a cheap trick here, right? T just is a variable representing the parameter, so we can call it whatever we want. So let's replace t with theta. If we replace t with theta, this is the same formula, integral from alpha to beta, square root dx d theta squared plus dy d theta squared d theta, right? We've changed nothing but just what we're deciding to call our parameter. So now let's keep this formula in mind. It's the same formula, but now we're using thetas. If you remember our formulas for going from polar coordinates to Cartesian coordinates, we have that x equals r cosine theta and y equals r sine theta. Okay, well, we're looking at some polar curve. We're looking at some curve r equals f of theta. So that means we can represent these conversion equations here as x equals f of theta cosine theta and y equals f of theta sine theta. Now, why do we want to do this? The reason we want to do this is because if we think about what we just obtained from switching out t for theta, we have a formula now for dx d theta and dy d theta. We just need to calculate the derivatives of x and y in terms of theta. So let's calculate what dx d theta should be. Dx d theta, when we take the derivative here, f is a function of theta and cosine of theta is a function of theta. So this requires the product rule. So using the product rule to compute the derivative here, we see that dx d theta is going to be f prime of theta cosine theta minus f of theta sine theta, right? So now we have a formula for dx d theta. Similarly, dy d theta is going to be f prime of theta sine theta. This is again by the product rule here. And then it looks like we'll have plus f of theta cosine theta. So now we need to take these representations of dx d theta and dy d theta and plug them in to our formula for arc length and see what we get. And so this is going to get pretty messy for a while because we have to take this equation here. We have to take this expression, f prime cosine theta minus f sine theta, and square it. And then we have to add that to the square of dy d theta. So let's look at what we have here. So we have L now equals the integral from alpha to beta. I'll just leave that open for now. We have f prime. I'm going to drop the of theta around the f's here to just save some room. So we have f prime cosine theta minus f sine theta quantity squared plus, that was dx d theta, and now dy d theta is f prime sine theta plus f cosine theta quantity squared. All of that is under the square root d theta. And now this formula is not helpful at all. In fact, it's more confusing or maybe less intuitive than what we started with. So let's see if we can expand these squares here and simplify. So I'm going to copy this down very quickly. Alpha to beta, square root. We add f prime cosine minus f sine theta theta squared plus f prime sine theta plus f cosine theta squared. All of that under the square root d theta, right? Yes. So now let's square the first piece. Integral from alpha to beta. I'll just leave that open. So it seems that we're going to have f prime cosine theta squared minus, then we're going to have the product of the middle term is going to be the product of f prime cosine theta and negative f sine theta. So that's minus f prime times f times cosine theta times sine theta. And then the last term is plus f sine theta quantity squared. So this is what happens when you FOIL dx d theta, right? When you have dx d theta squared, you FOIL that piece out. This is the result right here. Okay, and I'm going to do the same thing for dy d theta squared. I'll do it on the one line lower here. So this is all under the square root, right? So then we have plus, and now I'm squaring f prime sine theta. So I'm just going to write that as f prime sine theta squared. And now I have the product of f prime sine theta with f cosine theta. So this is plus f prime times f times cosine theta times sine theta. Okay, and then the last term is going to be f cosine theta squared. And so all under the square root d theta. Okay, and so now we look to simplify instead of complicate, right? And so what do we see here? We see we have a minus f prime f cosine theta sine theta plus f prime f cosine theta sine theta. So we see that this term actually cancels with this term, which makes our life a lot easier. We see also that we have an f prime cosine theta squared and an f prime sine theta squared. Well, these terms share an f prime squared in common. So we can pull out the f prime squared from that term. Similarly, we could pull out, so let's write that first. Let's first say this is the integral from alpha to beta, square root. These have an f prime of theta squared in common. And once we pull out the f prime squared, what's left? Well, from the first term, there is a cosine squared theta. From the second term, there was a sine squared theta. So that's what we get from here. And then we can do something very similar, but now with f squared sine squared theta and f squared cosine squared theta. These both have an f squared in common. So we can pull out the f of theta squared in common. And if we pull that out, what's left from the first term is sine squared theta. And what's left from the second term is cosine squared theta, d theta, right? In square root d theta. But now we see that sine squared plus cosine squared is 1, right? And we have that appearing twice. So everywhere there's a cosine squared plus sine squared, we just replace that with 1. And that means our integral is now much simpler. And it becomes f prime of theta quantity squared plus f of theta quantity squared d theta. And now we have a much simpler formula for arc length in polar coordinates. Let's take a look of a theorem. So let's let r equals f of theta be continuous on the interval alpha to beta, right? Then the length of our curve, r equals f of theta, between the lines theta equals alpha and theta equals beta, is given by what we just derived. And its arc length is the integral from alpha to beta of the square root of f prime of theta squared plus f of theta squared d theta. And another way to write this, if you'd like, is the integral from alpha to beta of integral of square root. So I'm going to flip the order of f and f prime here, but it doesn't matter. Addition's commutative. This is the same as r squared plus dr d theta squared d theta. So here we now have a relatively nice and concise formula for arc length in polar coordinates. And it was completely derived, if you remember, it was completely derived from the arc length formula of a parametric curve. So now we may use this formula to our advantage when trying to calculate arc length. So let's go over one example here. Example says find the arc length of the cardioid r equals 2 plus 2 cosine theta. Okay. So we need to find the arc length of a cardioid, r equals 2 plus 2 cosine theta. And we want to know the bounds for this integral, right? We have L equals integral. Let's just remind ourselves. Arc length is going to be the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. Okay, so we can compute the derivative of r with respect to theta, so we can plug in r squared and dr d theta, but we need to find the bounds. And when we start tracing out a cardioid, we start at theta equals 0, right? So when theta equals 0, r is 2. So we have something like this, and you can trace it out, and it's going to look something like this here. Okay, and we notice that as we go around the cardioid once, like as we make one full 2 pi rotation, we trace out the cardioid exactly once. And because of that, our bounds are just 0 to 2 pi, right? So that's just kind of how we can choose the bounds here, just kind of by thinking about what a cardioid actually does. And we know a cardioid is traced out once exactly as you complete 2 pi radians, right? And so now we just need to compute. So what's r prime here? It's going to be -2 sine theta, right? And so our integral now becomes 2 plus 2 cosine theta squared plus -2 sine theta squared d theta. Let's FOIL this out. So we get, when we FOIL the first piece, we're going to get 4 plus, and then it's 2 times 4 cosine theta, right? So it's going to be 8 cosine theta plus 4 cosine squared theta. And then we have plus 4 sine squared theta from this piece, right? This chunk here came from squaring 2 plus 2 cosine theta, right? And then the second piece came from squaring -2 sine theta. So d theta, right? And we see that we have a cosine squared plus sine squared after we pull out the 4, and then we can add the 4 to this 4 over here, and what we get is then the integral from 0 to 2 pi. So maybe I'll do one extra step here. It's 4 plus 8 cosine theta. We pulled out a 4 from the sine squared theta plus cosine squared theta, d theta, integral 0 to 2 pi. We know that this sine squared plus cosine squared is just 1 here. And so then we have a 4 plus 4. So our result is then 8 cosine theta plus 8. If we pull out a 4 from this piece here, then we have integral from 0 to 2 pi. We have a root 4 times root 2 cosine theta plus 2 d theta. but root 4 is 2. So we have 2 integral 0 to 2 pi integral 2 cosine theta plus 2 d theta. And so now this is the integral we're tasked with solving. This 2 cosine theta plus 2, all under the square root. And at first this looks a little tricky, but the reason I picked this problem is because I want to go over a trick that can be used to solve an integral that is of this form here. We have 2 cosine theta plus 2 under the square root. If you have something of this form, we can actually use a trig identity to our advantage. So let's remember the following trig identity here. Let's remember that cosine of 2x is equal to 2 cosine squared x minus 1, right? This is, maybe you've seen it written as follows. Cosine squared x equals 1/2 1 plus cosine 2x. Maybe this is a little more common of a way that you've seen it, this trig identity listed as multiplying the 2 over and then subtracting the 1 over gets you from here to here. So we're fine to express it in this way. We can add the 1 over and multiply both sides of the equation by 2 to get the following thing. 2 plus 2 cosine 2x equals 4 cosine squared x, right? So again, I just add the 1 over here. So plus 1, and then I multiply both sides by 2 and get 2 plus 2 cosine 2x equals 4 cosine squared x. Okay. But now, if I let theta, or if I let x be theta over 2, then we have 2 plus 2 cosine theta equals 4 times cosine squared of theta over 2. And remember, this is what was under the square root. And so we can replace what was under the square root. So our arc length is now the integral from 0 to 2 pi. Remember, here was our integral. So it was 2. Whoops. It was 2 times the integral from 0 to 2 pi of 2 plus 2 cosine theta. But we know 2 plus 2 cosine theta is now 4 cosine squared theta over 2 d theta. And so the trick here was to replace this 2 plus 2 cosine theta with things that are squared, right? I have cosine squared theta, which the goal was to cancel with the square root. And so now we can do that. So the root 4 will become a 2, right? So let's just do that first. We have 4, because it was 2 times this 2 here, integral 0 to 2 pi, square root of cosine squared of theta over 2 d theta, okay? And now we can cancel the squared with the square root, but we need to be a little careful because cosine is not always positive. So because of that, once we cancel the squared with the square root, we have to pick up an absolute value. Because again, cosine is not always positive. However, cosine is an even function. So because cosine is an even function, what we can do is, because cosine's even, we can double the integral, but halve the distance to only consider our positive values of cosine. And now the integral is much simpler to handle. We have 8 times, once we actually integrate here, it's going to be 2 sine theta over 2 from pi to 0, which is 16 times sine of pi over 2 is 1, sine of 0 is 0, and we get that the arc length of the cardioid is 16. Okay, so there's a nice example of using our formula for arc length and polar coordinates to actually compute arc length. So we had some cardioid, say like this, and we learned that the length or the circumference of this cardioid was 16. And again, I wanted to go through this example so we could see an example of solving an integral using this nice little trig identity and substitution trick here. So that wraps it up for what we'd like to discuss about polar coordinates and using polar coordinates to get new definitions for area and or new ways of computing area and arc length. Next week, we will jump to a completely new topic, kind of just totally switching gears here, and we'll start to look at vectors and vector valued functions. And Sophia will be giving those lectures. So then after Sophia gives those lectures, I will see you guys again when we start to talk about differentiation in a multivariable setting. So see you guys for now.